Okay, so on the assignment that I just gave back from yesterday, which at the time I only had half of your assignments. So on number 6, and you're missing this whole point of work, okay, in terms of what forces that you use and when there's positive or negative. So if you look on number 6, you've got a crate slides down a ramp, okay? So the motion of the ramp is down the hill, okay? So it's going down the hill, right? So again, any force in the direction of motion is defined as positive. Any force in the opposite direction of motion is defined as a negative value, okay? That's it. So, Paige pushes back on it with a 68 Newton horizontal force at an angle of 20 degrees. So she's pushing like this with the force of 68 Newtons, and that makes a 20-degree angle. Okay, so right away, she's pushing this way. What's the direction of motion? Opposite. So right away, your answer has to be a negative value. Now, the problem is mathematically, you don't generate a negative value. All forces that you calculate for work are always positive. You just have to decide in the context of the problem, do I make it negative? So here's the other thing, is that you've got a 68 Newton force, which is cool. But the problem is that that's not the force that you're going to use. You're going to use this, which is in the direction of motion. So you've got the cosine of 20 degrees, right? Mm-hmm. So basically you're trying to find the hypotenuse. If you look at the triangle, right?
So it should be 68 cosine 20.
No,
No?
it's 68 over cosine 20.
Because you're trying to find the hypotenuse.
I did a dumb.
Oh. Am I allowed to change it?
No.
Yeah, that makes sense. Fair.
Since it was due yesterday, I'm
Yeah.
glad you handed it in by the grace
I'll
of
just-
God. So, yes, you're trying to find that hypotenuse, not, yeah.
That's a problem.
You were treating it like the hypotenuse, but it's not the hypotenuse.
I did the dumb.
So you're gonna get this number, and then you just have to realize, oh, I'm gonna make that a negative value.
I did make it negative. It's just the wrong number.
Okay. Anyway, so that caused me pain and suffering. On the assignment from yesterday, because if 11A is wrong, everything is going to be wrong. So your answer to 11A should be a not so good GPA times 10 to the 8th.
Let's go.
Oh, yeah, I need to
Sounds about right.
that properly.
Because if that's wrong, everything is wrong. Your velocity on 11, Cohen, should not be 20,000.
It should not.
It should be between 100 and 200 meters per
Yeah.
second.
Yes, it should.
Oh,
Well,
I figured out why on number 3 on the last assignment was positive and non-negative.
okay.
Yeah, it's going.
I thought this was showing the direction of movement, but that's just
Anyway.
the friction.
So on the questions out of the book, so, and all of this is just kind of energy transformation questions. What page is that on? What pages are the questions in the book on?
311, 312.
Okay. So, on those questions, you've got,
What did you have?
so the brake shoes in your car made of material that tolerate very high temperatures that have been damaged. Why is this so? So, and this is what we're going to talk about today, is that the amount of energy in the universe is a constant.
Kinetic energy.
You're just changing its form. So if you look at, again, how your brakes work, you've got a rotor, and then around the rotor
Which, by
there's
the
a
way, I was doing
caliper,
momentum. You
and
can
that
see
caliper squeezes, and that creates thermal energy, creates heat, creates friction. So this is why if you ever, like, if you're up in the mountains and you're driving down, don't ride your brakes. Because if you ride your brakes coming down that mountain for an extended period of time, it can only withstand so much heat, okay? And if you ride them too long, literally, like, you'll be able to smell your brakes getting hot, okay?
If you go down,
Shift down into a lower gear and let the transmission do the work. Don't let, or at least if you can do that, then at least every once in a while, like, hey, pull off to the side of the road, let your brakes cool down.
if you go down Pikes Peak, they have a mandatory brake check about halfway down, where they stop your vehicle, they check the temperature of your brakes, and it's over a certain amount, you have to pull over and let them cool. And the lady in front of us got like a wild number. Like, the guy took the temperature gun to it and was like,
Yeah, this is a catastrophic failure. But the same thing happens, though, if you look at, like, let's say, for example, you talk about the Apollo 11 missions or anything returning back to Earth, right? Well, conveniently, we have an atmosphere, which is kind of cool, because without it, we wouldn't be here having this discussion. So this thing is coming in with a tremendous amount of kinetic energy, okay? It's going really, 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 really fast. So you've got to basically drop that kinetic energy to zero. So when it hits the atmosphere, then this is why you have heat shields and thermal tiles and everything else. Because basically what happens is that it hits our atmosphere, it begins to heat up. So what you're doing is you're exchanging kinetic energy for thermal energy. And so, okay, great. So this is also why it's like the most dangerous part, because if there's any compromise to the structural integrity of the bottom of that shield, and that's what happened to one of the space shuttles back in, I don't remember what year, but they had a hole in the leading edge of the wing, and as it re-entered into the atmosphere, that leading edge started to get hot, all that thermal energy went into the inside part of the space shuttle, and unfortunately it disintegrated and basically fell over the state of Texas. And people saw it, it's like, oh my God, here's a streak of light. Well, that shouldn't be happening. And so that's always the most dangerous part. Out of the book problems, number 8, that answer should be around 30. And your answer to number 12 should be between 800 and 900.
Okay.
Is that a good enough gap,
I had a good assignment. I'm just writing it down.
Okay. I need to change my answer.
That's a really good gap. So just looking at it.
Oops.
It's not between 10
I
and
didn't know if you wanted
Yeah.
it back in.
and it's also
Okay.
not negative 1440.
Yes. Just
Any-
divide that by 2.
Any
You're
other
good.
questions on that assignment?
Oh! Wait, no, this has to
He
be
forgot to multiply by a half.
for, what is it?
That
B squared.
Okay, anything else? Going once, going twice? So,
Oh yeah, because it's work.
You can kinetic energy.
And actually velocity needs to be squared. So that's 1/2.
Ooh. The square velocity. I might have forgot to square velocity. Potentially.
It should be 864. So if it's got a velocity of 864 joules, then she needs to put in a velocity of negative 864 joules. Yippee!
Set to 860.
And that is an answer between 800 and 900, not negative 1440.
Yeah. I just forgot to square a number. But we're good.
So this number divided by
Whoa.
500.
whoa,
That's a lot of letters.
that's a lot of letters.
Nuh-uh.
That's a lot of letters. Okay.
This is so unfortunate. I'd use an entire page for one problem.
All right, so we're into like the second great conservation law, third. Conservation of linear momentum, conservation of angular momentum, conservation of energy. So all of these problems are pretty idealized situation in the sense that when you look at energy being conserved, it's kind of has that same general format that, hey, the amount of linear momentum before has to equal the amount of linear momentum afterwards. If you have a certain amount of angular momentum, you have to have a certain amount of angular momentum afterwards. So the same thing is true of energy. But here's the problem with energy, is that energy takes on so many different forms. You can have kinetic energy, you can have rotational kinetic energy, you can have energy stored in a gravitational field, you can have energy stored in a spring. You can have thermal energy, you can have sound energy, you can have all these different types of energies. And so momentum is relatively simple, because momentum is like a one-trick pony. It's just mass times velocity. You can't have different forms of linear momentum. That's it, it's just linear momentum. And the same thing is true of angular momentum. Oh, okay, hey, the wheel was spinning, here we go. But with energy problems, because it can take on so many different forms, that's why it makes it a little bit more complicated. But the beauty of it is that it's all the same idea, okay?
Work equals force times.
The only thing you can do is just change forms. The only problem is that you have more forms that you can deal with.
Work equals force
So
times distance.
what I have
Work
written
equals
out
force.
is this big whole complex
If you want to
thing,
go to rest, you need
which basically
that many-
says, hey, here's the four primary types of energy that we're gonna have.
that many joules.
So you can have
You need
UG,
that many meters.
which is gravitational
You
energy,
need that many newtons.
US, which is the energy in the spring, translational kinetic energy, which is just the apple moving, rotational kinetic energy, that's if the apple's gonna spin, and then you have the new gravitational potential energy, the new spring energy, the new translational kinetic energy, and the new rotational kinetic energy. Now, for the sake of today's assignment, we're not gonna have to worry about us. We're not gonna have to worry about rotational. So the S's and the KR's for today aren't part of the story, okay? They will be
It's just
part of the
long
story.
distance.
They're just not part of the story
That's why
today.
it's not the same.
So, and it's just like momentum problems. Momentum problems in and of themselves aren't difficult. Where you
Mass
run
times
into trouble is
velocity.
if you try and get cute and you shortcut the process. The same thing is true of momentum problems, energy problems. Energy problems aren't tough unless you try and get cute. So, we're gonna start off with a simple example. So I've got this tennis ball and I'm gonna hold it up to a height of 2 meters, okay?
Okay.
So here's this tennis ball.
Good.
It
tennis ball.
is, has a height of 2 meters above the ground, and let's say that it has a mass of
2 tons.
or 0.1 kilogram, whatever.
That's close
Okay?
enough.
Close enough. So and the other thing that you're seeing is that I'm gonna work this from an energy perspective. So all I wanna kind of do is give you a different way to analyze this problem. So what I would recommend, okay, is that I would set up a chart, and if you look at how I work these problems. So in this situation, I'm gonna hold it up here. We're not gonna talk about it rotating.
Perfect.
There's no springs involved, so we don't have to worry about us.
Yeah,
So
just use the book
this type of energy is only going to involve UG and KT, come on, and then the sum of these energies. So what we're gonna do is look at 3 different situations as this ball falls. We're gonna look at what's gonna happen at the top. We're gonna look at what happens when it hits the ground. And what happens when it's at a height of 1 meter. Okay? Here we go. You don't have to draw these charts, but I'm gonna tell you right now, as we get into more and more complicated problems, if your answers are wrong, and you hear me out right now, if your answers are wrong, and I can't see a chart, and I can't see what you've done, and all I see is random gobbledygook numbers off to the side, I'm gonna tell you right now, I am not gonna waste 1 second of my life trying to sort it out. So if you don't wanna draw the charts, that's cool. You all are big people. That's the decision you're gonna make. But if your answers are right, that's cool, okay? That's great. But if your answers are wrong, I am not even gonna try and give you partial credit, okay? I am not going to try and figure out what you did wrong, where the math went wrong, nothing, okay? So just be aware that that's the deal. And we're gonna be dealing with some fairly complex problems. So if you choose not to do the chart, that's on you. But how I grade it is on me, okay? So just keep that in mind. All right, so I've got the ball up here. Cohen, what's the only type of energy that it has?
Potential.
What kind?
Gravitational potential.
Right? So up here at the top, it's 2 meters above the ground, and it has a mass of 0.1 kilogram. So knowing that information, Cohen, can you calculate the UG?
Sure.
What's it gonna be?
The mass times gravity.
Yeah, so my UG is gonna be the mass, 0.1 kilograms, times G times
Distance.
2 meters. Now, UG is a scalar quantity, okay? It's just a number, just because that way it's consistent. KT, translational kinetic energy, is just a number because it's 1/2 mv squared. Rotational kinetic energy, boom, there you go, 1/2 I omega squared. So all these, you don't have to worry about making negative. Don't go, oh, that's negative 9.8. No, it's energy, okay? So if you do this, you get 1.96 joules, okay? Right? Now, is there any kinetic energy at this point?
No.
No, okay? So
Sure.
this is OJ, right? We got nothing in that column. Nothing is there. So at this point, I get this number 1.96 joules. This is the most significant this is the most significant number in this problem. Because what that means is that afterwards, this sum, no matter what happens,
That'll
has
be
to
that.
add up to 1.96 joules. Okay?
Otherwise, energy is just poof.
Yes. And we're going to assume that we're not losing any energy to friction or anything like that. So, but here's the problem. If there's ever a number that you like double check, it's this number. Because if this number is wrong, everything is going to be wrong. Okay? Everything is going to be wrong.
Bad.
So,
Bad.
if you're into the idea of containers, and some people like this analogy. So I've got an UG container and I've got a kinetic energy container. Okay? So at this point, my UG container is filled up to a 1.96 joule mark. My kinetic energy container is empty. So as the ball falls, imagine that there's a siphon that's going to move the energy from the UG container over to the kinetic energy container, right? If you're into graphs, it's like, oh, Burkamp, I was president of the graph club in high school. Fine. Okay? So you're gonna start up here with a certain amount of UG. Kinetic energy is gonna start down here at 0. Kinetic energy is gonna go up, UG's gonna go down. At some point, will those lines cross?
Yes.
Yes. Okay? Those lines will cross at some point. And when those lines cross, what's gonna happen?
It's gonna hit the ground.
No.
Well,
Yes.
let's say they cross right here.
Mm-hmm.
Is UG
Oh.
a non-zero value?
Oh, it's at 1 meter. Oops. And then it's UG is 0 when it hits the ground.
Ah.
There we go. I did it
You're
dumb.
thinking now.
Yes.
Ah. You've become possessed by the spirit of Cohen. That was a Cohen answer right there. Bad. Yeah.
You're using your decoration brain for something.
Okay.
My brain just sits up there. And
Now. So at this point, it's all up, right? Now, I drop it, boom, begins to fall. So when it hits the ground,
Mm-hmm.
how much UG does it have?
0.
Why?
There's no distance.
Because
Their height is 0, right?
Yep.
Don't make this complicated, H is 0. So that's OJ.
So
So how much kinetic energy are you going to have?
1.96.
1.96 joules. Yes,
Otherwise,
everything still
I
has to add up
Very
to
wrong.
1.96.
1.96 joules. Now, at this point, can I calculate how fast the ball was going when it hit the ground?
Yes.
Why?
1/2 mv squared.
Because you know kinetic energy
And
It's about relativity.
equals 1/2
no mass.
mv squared. Do you know the kinetic energy?
Yes.
Yeah.
You know the mass.
Yeah.
Yes.
So, Preston, solve that for velocity.
The square root of 2k over mass.
Beautiful. So, velocity is the square root of 2kt
Good old
over
algebra.
mass.
Good
Okay?
Old
Cool,
algebra.
got this, right? So, somebody take 2 times that kinetic energy of 1.96 joules and divide that by the mass of 0.1 kilograms. What do you get?
What is that?
6.26.
6 point what?
6.26 is what I got.
6.26?
Wait, is that one? Yeah, that's 1.96. Yeah. Yeah, 1.96.
Okay,
Over-
You're right.
Yeah.
cool. Now, we're gonna do the same thing.
Yeah, I could just.
But now we're gonna use Hank,
Uh-oh.
Oh man.
okay? Now we're gonna use Hank.
Pass.
What numbers are going to change? So let's say that
Mass.
Hank has a mass of, we'll make the math easy, 5 kilograms.
How many pounds is he?
I don't know, that would be about 12 pounds.
Roughly
4.9 joules.
So,
11.
am I gonna have more UG?
Yes.
Yes.
Mhm.
Am I gonna do more work to lift Hank up?
Yes.
Very
Yes.
much so, right? So,
I would hope.
somebody take, so now my new UG
5.4.
is gonna be 5 kilograms times G times 2 meters, which, check my math, should be 98
Oh yeah.
joules,
Yep.
right?
Yup.
Cool with that?
Yes.
Sure.
Okay. So when Hank hits the ground, how much kinetic energy is Hank going to have?
98 joules.
Kinetic energy is going to equal 98 joules. Cool. So that's using Preston's equation of V equals the square root of 2 kt over m. Cohen, take 2 times 98 joules, then divide that by 5 kilograms, and let me know what you get.
6.26.
Shockingly,
Whoa.
we get the exact same velocity.
That is because gravitational acceleration is a constant.
That equation.
Okay, we'll talk about that equation in just a second. Okay, we'll get to that equation. So, here's the story. If you were to look at, if this is the UGG line, the kinetic energy line for Terry the tennis ball.
Travis.
If you were to draw that same graph for Hank, how would the graph change? Or would it? If that's Terry the tennis ball, if you were to draw a kinetic energy time graph or an energy time graph for Hank, would it be any different?
The slopes.
Time changes at a faster rate? Or
What?
you can you said
Time
the slopes.
changes at a faster rate.
When he said the slopes, my brain just shut off.
It'd be
How maybe energy?
I'm thinking.
Is it greater?
Okay.
the energies
Well,
are greater.
Cohen, you were actually on to something. You just said it wrong. Okay, that's never happened before. So, instead of starting at 1.96 joules, where's the Hank line gonna start?
96.
98?
98, yeah.
Whatever. What's a couple of joules between friends? So, it's gonna start way up here at
98.
98. Is it gonna go to 0 at the exact same time?
Yes.
Why?
Because it
It
falls
falls.
the same.
the
They
same
accelerate
size
at the
as
same rate.
So,
So, the Hank line
it's going to be way steeper.
would go something like this.
That's what you mean by
So
that.
the rate of change in energy per unit of time is going to be much bigger, right?
Mm-hmm.
So when it lands, is it going to have more kinetic energy?
Yes.
Yes. This is why I'll drop the tennis ball on my hand, but I'm not going to drop Hank, okay? Because Hank's going to have a lot more kinetic energy. Hank's going to have a lot more momentum. Now, we have 2 more pieces of this puzzle to fit together. What would a momentum time graph look like now that we know the velocity? So what would a momentum time graph look like for Terry the tennis ball? It lands at 6.26 meters per second.
Mass.
It has a mass of 0.1 kilograms.
So 0.6
So if I take 6.26
times
meters per
0.1.
second
So 0.626,
times 0.1 kilograms, check my math, I get
0.626.
0.626, right?
Mm-hmm.
So let's call that 1, right? And that's going to be a certain amount of time, right? Okay. Now, let's talk about time. Is the time going to be the same for both objects?
Yes.
Why?
Because gravitational acceleration is a constant.
Right? So, Cohen, let's talk about the time. So,
It is
we can do 2x over g, the square root of that, to get time, which would be 2 times 2 meters divided by g, which gets me, what,
4 over 9.8, so 0.638.
0.638 seconds. Okay? So it's going to land with a momentum of 0.626 Newton seconds, and that's going to take 0.638 seconds. What does the slope of a momentum time graph give you?
Force.
Can we find the slope of the line?
Yeah.
Cohen, find the slope of the line.
Well, we have. Oh wait, it's just the point.
Cohen, you're making this.
I'm making this too hard.
Change in y over change in x.
Change in y is.
0.626.
It's about.
I'll pull the full values.
Wait, what is this?
It's about 0.1.
0.626 divided by.
0.638
What
seconds.
does the slope equal?
Force?
Force?
I gotta have this somewhere. I don't.
What's the
That's
area
weird.
under?
No, you
Oh,
seconds
no,
over
you
seconds.
0.638
What's the
is
area
about
under?
1.
Oh, no.
What do you
no,
get?
force.
1.
Exactly.
Yeah.
You took 0.626 and divided by 0.638 and got exactly 1.
No, I took 0.638 and divided it by 0.638, which is not what I was supposed to do.
It should be about 1.
I was trying to pull the full value. Oh, I'm literally stupid. 9.8.
9.8.
Exactly.
You took 0.626 and divided it by
What are you talking about?
0.638.
Oh my gosh. No, I took 6.26 and divided it. Gapshawn, this is why you're supposed to do this.
It's 0.981.
Oh, you get 0.98. What? Newtons. Oh, what does the slope of a velocity of a
I got it. I got
time graph
0.98.
give you?
I got 0.98 this time, guys.
Oh, you got 0.98. Why'd you get 0.98?
I don't
That's
know.
gravity.
What's the force acting on Terry the tennis ball when you drop it?
Oh,
point.
Gravity.
I'm just, yeah.
Now,
Yay!
yay for math.
Good job, Cohen.
Now, let's do the same thing for Hank. We got 6.26 meters per second. He has a mass of 5 kilograms.
I don't think
Let's try to do this the first time, Cohen. Take 6.26 times 5.
Yeah, 31.3.
31.3?
Yep.
Solid.
Yeah.
Okay.
Very
Now,
solid.
this is going to be way up here at 31.3. This is the Hank line.
I pulled the full
Why is the Hank line steeper?
value.
Because it has more mass.
Because he's thick.
I have no idea what you just said. I
Good.
don't know if it was Stick or Hank. I don't know.
Both.
Both. So, what's the slope of that line going to be?
Is you
B.
no?
Wait.
Oh, 0.98 times 50. So like 4.9. No. Yeah, 4.9.
49.
49 newtons. Why?
Because 9.8 meters per second squared times 5 kilograms.
Is 49 newtons.
Because only force is gravity.
Yes.
Good job, Cohen.
I learned something.
Hey, we do it without the calculator this time.
Now,
Did we put it in the calculator?
if you were to draw a force time graph, how would the force time graphs be different? Or would they?
Well, Hank has
There'd be
way
force
more
on
force.
Okay, so here's the tennis ball line, which would be 0.98 newtons times
The
The 0.638 seconds.
Yeah.
0.638 seconds
and Hank would have 49 newtons.
In the same amount of time.
in the same amount of time. So which one undergoes a greater change in momentum?
Hey.
Hank does, because that's a bigger force acting over the same period of
Time.
Get this. It's exactly 50 times more.
wow,
Oh.
oh, shocking.
Wow.
So really, we just need to
Now.
ignore everything else and only focus on maths.
Well, if gravity.
Let's go old school. That equation.
Hey.
Oh man.
It's a boy.
Hey. So
There he is.
let's say you're getting ready for the acceleration test way back in the day. Okay? Back when life was simple.
And happy.
I'm just telling you, you're getting ready for the acceleration test. I drop a ball from a height of 2 meters. How are you going to find the velocity when it lands? So it's the only thing that you need.
Mass. No. Distance. Distance. Distance.
Distance and your gravitational acceleration, right? So my initial velocity is
I change inches really fast.
0. True. So I got v equals the square root of 2ax. So if I take 2 times 9.8 meters per second squared times 2 meters, Cohen, what do I get?
6.26.
Oddly enough, I get 6.26 meters per second. Cool. Okay? And here's the reason why. I can't have a set of energy equations saying, oh, the velocity is 6.26. And then I work with kinematic equations going, no, the velocity is 8.26. And it was like, okay, well, this sucks.
Average.
Yes.
Average of
Oh,
error.
timing error, human error. There we
Human
go.
error.
We'll take the average of the two. So I can't have the kinematic equations of physics say I get one velocity, and the energy equations say no, you get something completely different. Okay? Cool. Now,
So what I'm hearing is we should just use the kinematic equations.
no.
Well, it depends on what information you're getting.
Now, I want to figure out what's going to happen. We're back to Terry the tennis ball.
Hey, Terry.
I want to figure out when it crosses a height of 1 meter. Okay, so this is crossing the 1 meter mark. Okay? When it crosses the 1 meter mark, I want my UG, my kinetic energy, and my velocity when it crosses the 1 meter mark. Okay? Cool. Now, what do my two energies have to add up to?
1.96 joules.
1.96 joules.
Otherwise, you go to physics jail.
Exactly. So, if it's at 1 meter, and it is, Preston, what can I find?
Velocity.
I can, but that's not what I want. Energy. Do I know a height?
Yeah.
1 meter. Do I know the mass of a tennis ball? Do I know what G is? Right? So at the 1 meter mark, I can find my UG. I can take 1 meter times G times 0.1
What a polite
kilograms. Huh?
Yeah, it's unlocked.
Yeah, oh no. Hi, are you doing observations?
Yes.
Okay, welcome.
Thank you.
Thank you. You can just kind of sit wherever you feel comfortable. This is my testosterone-laden AP Physics class. And we're discussing conservation of energy. She is going to Butler County. You were a Grizzly
Yes, miss.
and taking education classes. I was a Grizzly for a year. Thank you very much. And so, and your name is?
Ariana.
Ariana. Okay, Ariana is doing some observations on different teaching styles. So that is why we are blessed with this young lady's presence.
Uh-oh.
Okay. Be in the
That's
best
not good.
behavior. All right. So,
And guys.
if I take 1 meter, which is how high the tennis ball is, times G, times the mass, what do I get? You are not going to use a calculator to do that calculation.
Point,
It's 1
0.98.
times 0.1 times 9.8.
0.98.
0.9.
0.98 joules.
You would count.
And? Calculator.
So,
My
Will,
calculator is my
here's your moment to shine.
Oh, yes.
This game makes no sense.
So if UG is 0.98, what's my kinetic energy?
0.98.
Oh, are they equal?
Yes.
Yes.
Oh, how cool is that? Now we split the two, right? So the UG container is now dropped to 0.98 joules, and my kinetic energy container is up to 0.98 joules. Cool, got it, great. Okay,
Golden.
now, how fast is the tennis ball going when it lands?
6.26.
6.26, right?
We did this, man.
So when it lands, the tennis ball is going to be traveling at 6.26 meters per second. At the 1 meter mark, we said the UG was 0.98 joules, and the kinetic energy is 0.98 joules.
3.13 meters.
So here's the question.
Calculator.
Here's the question. At the halfway point, here are your choices. The velocity is, if you take half of that, you get
3.13.
3.13. So one option is the velocity is bigger than 3.13 meters per second. So that's choice A. Choice B is, since everything is getting split, the velocity is just going to be 3.13 meters per second. Or option C, it's actually less than 3.13 meters per second. Cohen,
B.
B. So how many vote B besides Cohen? Cohen's the only one on the B train.
What?
Yeah.
He is.
Remember
He
the
is.
equation,
He
Cohen.
is. He is.
Oh. I'm leaving the B train.
No. B train has left the station.
I'm jumping off the moving B train.
Why are you willing to sacrifice life and limb to jump off the B train?
Because kinetic energy equals 1/2 mv squared.
You're right. It does.
Mhm.
So, which train are you jumping on, the A train or the C train?
I'm just gonna sit in the station for a little while.
Think about your choices.
Think about your life choices.
I'm just gonna wallow in my regrets for a little bit, and then
Well, that's
Jump on the
comforting.
tracks.
Once you get out of high school, the ability to wallow in my regrets. Fantastic. Gap Sean, you're on the C train. Why the C train?
oh,
1/2 mv squared, and because acceleration, there's in less time, it's an exponential relationship between velocity and time.
So it's the next one. So you're on. So Gap Sean's on the C train. Will Stanley,
I'm also on the C train.
Danny,
I'm also on the C train.
Colin, you're still in the station.
C train.
You haven't seen. You don't even know the trains left the station, man. Okay, so you all are on the C train.
also we're gonna lose energy once it bounces. So
Oh no! No!
No.
No,
We're assuming
not
no
talking about the
reverse.
bounce. No bouncy balls. No.
Oh, it
this is
hasn't
just
bounced?
Boom. on the
Oh,
way
this
down.
it's literally just fallen.
We
Just
are not-
fall
we are
and
not
it
momentum.
hits the ground and we don't do anything after that.
We are energy,
Okay.
not momentum.
Okay.
Leave the last.
Now, how can we settle the argument?
Just solve.
Solve
We're going to use the Preston equation, right? So velocity is the square root of 2 times your kinetic energy divided by mass. True?
it. Yes.
Sure.
So we have 2 times 0.98 joules because that's what Will Stanley said it was.
I did not.
And we divide it by the mass of 0.1
Uh-oh.
kilograms. Oh, Gap
no.
Sean!
Oh, no.
Oh, Gap Sean! What
Uh-oh.
did you get?
I'm jumping on the A train.
You got 4.43 meters per second.
I watched you all load the
Wow.
train.
You all jumped on the wrong train.
You jumped on the wrong train too,
wait,
Cohen.
wait.
Oh,
I was
wait.
closer.
It's gonna travel the other distance in a faster amount of time.
Oh,
Yeah.
why?
Because it's accelerating.
It's accelerating.
Yeah. Okay. I don't know why it's less.
But no. You don't need to cast wads of paper at anyone, okay?
I was closer than he was.
That's actually valid. Okay,
Valid, but still
Yeah, I can
wrong.
see where-
so does velocity, speaking of acceleration, does velocity change as a linear function of time or a linear function of distance?
No, what?
Sorry,
No
ask the
linear.
question
No
again.
linear.
But slower this time.
Does velocity change as a linear function of time or distance?
This time.
No.
AT.
V equals V naught plus what?
AT.
AT.
I'm not the super
Wait.
guys.
It changes as a linear function of time. Which takes longer to fall, the first meter or the second meter?
First meter.
First.
Why?
Because it's going from 0 to it's not very fast, and it's accelerating, so it gets faster once
So
it
it
does the
takes
second one.
longer to follow the first meter,
Yes.
true?
Oh, that's
Yeah.
for work.
Bro, I don't know what I was thinking, but it said less.
It takes longer to follow the first meter, so therefore you're going to have a bigger change in
Velocity.
velocity. Oh my God. No.
Stop throwing wants of paper.
Yeah,
1-3.
okay, so stop that, let's kind of regroup, now that I'm gonna